Hello everyone and welcome to today's webinar. I'm Tom Floyd. I'm your moderator for today's session. With me are two fantastic panelists. We have Sue Poniatowski from High Speed Data Path Applications. Good morning. And Alex Tan, High Speed Data Path Marketing. Welcome.
Good morning.
And one quick housekeeping thing, as always, to keep in mind before we get started with our conversation today. For those of you who are joining us live, we really want you to ask a lot of questions. So make sure to type those to me directly if you're logged into the GoToWebinar interface, and I will ask those on your behalf. And with that said, I think we can go ahead and get started. So take us away.
Super. Well, thanks for joining us today. And before we get into the objectives, I'd just like to remind people that this is actually the second webinar in the series on automotive FPD-Link products. So for some of the basics of FPD-Link, please feel free to go back and check out our first webinar that John Goldie and I gave earlier this year. So the objectives of this webinar are really to start to talk about a new product that we're going to be launching in September. It's the DS90UR905-906 FPD-Link II chipset. We're going to talk about the enhancements that this provides over the prior generations of the FPD-Link II chipsets, and really go into detail on the main features and their value to the system. And finally, we want to make sure that people understand the key benefits that the chipset delivers. So first, we're going to talk a bit about automotive applications. And Sue, if you would, just kind of set us up here.
Yeah, sure, Alex. I'll just go over the basic application here. With the FPD-Link II serializer and deserializer. The goal is to send high-speed video data over a single narrow interconnect over a fairly long distance, taking the data from the host graphics processor to the display. In the case of the 905 and 906, we're now supporting a 24-bit color interface. This means we're sending 8 bits of red, green, and blue data. This goes into the serializer. It's sent across a single pair interconnect to the deserializer, and then the parallel outputs of the deserializer go to the display.
That's right. And the 24-bit color, this is new for us, right?
That's right. It's an upgrade to our previous generation that supported 18-bit color.
Super. So what applications would you use this for? Well, it really is targeted at the automotive display market. We've had a number of FPD-Link products, like we talked about in the last webinar, that have gone into these areas, and we've learned a lot about what customers are really looking for. And some of those target applications include the central information display, which is in the center of the car, rear seat entertainment, that's for the kids, right? And then navigation, so that the driver doesn't have to look bad when they lose their way. One of the big changes, like Sue had just mentioned, is that it supports both 18-bit and 24-bit color depth. And the higher color depth really makes for a better picture. And finally, it supports much higher resolutions than the older chipsets, up to the 64 megahertz pixel clock. So some of the resolutions that we support include the WQVGA, which is a 400 by 240, all the way to the XGA at 1024 by 768.
Now, which of these are the most common resolutions for automotive applications?
That's a good question.
Yeah, so what we see very commonly are the 800 by 480, and that's something that Alex and John talked about during the last presentation. But what we're supporting with this chipset is actually the full range down to the wide quarter VGA, which are very common for some small central information displays. And then going up to what we call the dual view wide VGA. Now this is really interesting. This is where you have a single display in the center console of the car, and both the driver and the passenger can view different content on this display. And then finally the XGA resolution, which is more used for the rear seat entertainment, and it's a bit higher resolution than what we've seen in the past.
Okay, great.
So it's really exciting, and one of the key takeaways here is that the FPD-Link to the DS90UR905-906 really spans the gamut from these rear view cameras to very fancy systems where, like Sue was saying, two people can watch two different things at the same time.
Great.
I'm looking forward to that one.
Yeah, definitely.
All right, so let's dive a little bit into what we mean when we talk about 24-bit color and color depth. This is an illustration. I hope you all can see this clearly on your displays. We're showing the differences between a low color depth and a higher color depth. Just a quick update, if we're talking 1 bit per pixel, then we're talking just a simple black and white display. If we're talking about, for instance, 18 bits per pixel or 24 bits per pixel, we're getting into higher color depth. 18 bits per pixel gives you 262,000 colors, and 24 gives you 16.7 million colors. The great thing here, once you get to this true color, 24-bit color, is you're beyond what the human eye can see. So you're sure to cover the full gamut of colors that the human can see. What we're showing here in the illustration is a difference between an 8-bit per pixel and a 24-bit per pixel. And on the top graphic, you'll see that as you transition from a lighter shade of color to a darker shade of color, you will be able to see banding during those transitions, or lines as you go from dark to light. In the case of the lower graphic, 24-bit color, now you can have a gradient going from dark to light, and the transitions are very smooth. This is really important even on low resolution displays when you have, say, a graphical data that's being put up and there's a gradient of color. For instance, a logo for the automotive OEM,
Yep.
and the background may be shading from a dark blue to a light blue. That'll be a very smooth transition, and the user won't be distracted by any kind of lines or bars as the color gradient changes.
Yeah, it's pretty amazing how many colors the human eye can see. You don't think about it, right? Millions or tens of millions. So let's talk about some of the other enhancements on the part.
Sure, so right here I'll just walk you through the changes to the 905, 906 with respect to the earlier versions of our FPD-Link II chipset. So starting with the serializer, as we mentioned earlier, we now support 24-bit color as opposed to 18-bit color. The pixel clock range has been extended, so now we go all the way from 5 megahertz, which supports the lower resolution displays, all the way up to 65 megahertz, and that's enabling, as we mentioned earlier, the dual view displays and also XGA displays for rear seat entertainment. Now moving on to the interconnect, a couple things we've done here. Remember, we're running higher speeds and we want to still support the long 10-meter cable length or longer. So we've added some signal conditioning. This includes de-emphasis at the serializer output and also equalization at the receiver input. We've also integrated the terminations, allows for really simple board design, not a lot of components. We've enhanced the built-in self-test mode. This allows the serializer to generate a pattern, and this is tested at the deserializer for kind of a self-enclosed test system and validation of the link between the serializer and deserializer. We've added an optional I2C control interface. This is in addition to providing the control for configuring the devices via pins. Now you can do this via an I2C bus. So a simple cable connection allows the user to configure the device differently depending on how it's being used. And finally, we've added a true spread spectrum clock generation at the outputs of the deserializer. And this is really targeted at reducing EMI at the parallel interface between the deserializer and the display.
So if we look at it, what we've done is we've increased the bandwidth, increased the speed, but to be able to do that and still meet the EMI requirements of an automotive application, we've added in a number of new EMI mitigation techniques.
Exactly. We've added EMI mitigation, and we've added some signal conditioning to accommodate sending the higher bandwidth over the same long single differential pair.
So we're really excited about this part. And before we go into detail on some of these features, let me go ahead and just talk about what are the key features here. We've got the SerDes and LVDS, which gives us the single pair link. And we have to remember that that's really the key feature for the automotive application. We've got the wide pixel clock range going from 5 to 65 megahertz, 24-bit color support with the vertical sync, horizontal sync, and data enable built into the signaling. Signal conditioning for extended length interconnects going greater than 10 meters. And that's for both on the serializer with the VOD cell and the de-emphasis, and also on the deserializer with the equalizer up to 12 dB boost. And EMI minimization features, so the true spread spectrum clock generation DES outputs, which is the SSCG outputs.
Can you tell us a little bit more about what you mean by true SSCG DES outputs?
Sure.
Yeah, sure. So the spread spectrum clock, and we'll have another slide that describes that a bit more later, is slightly moving the clock at the output to reduce the spectrum of noise. Okay. And in addition to just moving the clock, the data, so remember we have 24 bits of parallel data, that's also moving with the clock. So what that does is it reduces any noise that occurs at a given frequency, spreads it over a broader spectrum, and reduces the EMI at that interface.
Okay. Gotcha.
The way to think about that is that you have all of these bits transitioning at the same time. If they exactly transition at the same time, that has a big impact on the EMI. So the spread spectrum clock generation allows that to be moved out in a more pseudo-random or more effective way.
Got it. Okay.
Other features include a new BIST mode with factory test and diagnostics, the optional I2C control that Sue mentioned earlier, and also we do have AEC-Q100 level 2 qualification on this part, which really is an absolute requirement for auto infotainment systems.
Okay, so you've probably seen something similar to this in the previous presentation on FPD-Link II. Here we're going to show some of the differences with this new 905, 906 chipset, which is generation 3 of the FPD-Link II interface. We're preserving the same 28-bit payload that we've had previously, and you'll note we're sending 24 bits of color, 3 control signals, as well as the overhead bits. So let's just step through these. We're starting off with the clock 1 and clock 0 bits, and those provide the transition so that the deserializer can extract the clock. We also have the DCA and DCB bits, which are the overhead bits we've had before, but now we're adding something to them. We're including the vertical sync, horizontal sync, and data enable signals embedded within the transitions of the DCA and DCB bits. What this does for us is this frees up the additional 24 bits to support just the color data that's being sent over. In previous generations, we had the 18 bits of color data, plus we had separate bits allocated to the H-Sync, V-Sync, and data enable. So now all 24 bits are the color information. The payload bits, as before, they're still randomized, balanced, and scrambled. And what this does is it provides DC balancing for an AC-coupled interconnect, and the randomization and scrambling guarantees good eye openings and also minimizes EMI on the interconnect. Now we've gone from an 85% efficiency to a greater than 85% efficiency with the embedding of the sync signals within the DCA and DCB. Okay, moving on to the next thing, I'm talking a little bit about the interconnect and how we've enhanced the signal conditioning to allow us to drive the long distances with the higher data rates. So at the serializer, we've added a de-emphasis feature. Now what we're showing here on the right is an example of how de-emphasis works. And so we have a series of transitions starting with the pattern going from a 0 to a 1, then to 3 zeros, and finally another 1. If we refer to the letters at the bottom, we'll just walk through the transitions here, looking at the single-ended signal at the top and the differential signal at the bottom. So for the first transition, first signal, we're sending a 0. We're swinging to the full differential swing. Again, a single 1, we're going to the full differential. Then we have a series of zeros in C, D, and E time frames. We're swinging the full swing on the first 0, but then you'll notice that we back off. This is where we're using de-emphasis. The second and third zeros in the sequence, time slots D and E, we've now backed off and we're de-emphasizing the signal. The idea here being we don't want to continue to build up too much charge on the cable. This allows for an easy transition to that final 1 bit that we're sending in time slot F. The overall impact of this is that we get a nice clean eye opening even when we just have single bit transitions following a long sequence of 1s or 0s. In the 905, 906 chipset, the de-emphasis level is programmable, so that allows to adjust the level of pre-emphasis to be optimized for the cable that you're driving.
So just to kind of summarize, this graphic is really showing where that de-emphasis is happening.
Exactly. And then moving on to the deserializer, we've added an equalization feature, which is something new for the FPD-Link II interface. And this equalizer option, again, it's programmable. It allows you to select anywhere from 1.5 dB to 12 dB of gain. Again, this needs to be configured to compensate for the particular cable and frequency that you're driving. One nice feature we have here, we have a couple of test outputs that let the user view the output of the equalizer. So imagine the signal is going into the equalizer and the eye pattern looks very bad. These test outputs let you look at the quality of the eye signal after it's been equalized within the receiver. And this helps the user and us as well in our evaluations to determine the right amount of equalization to use for the interconnect being used.
So these features are really designed to push the length and preserve the bandwidth.
Exactly. Particularly as we increase our data rates, then we need to use these features to guarantee an open eye at the receiver end and good data sampling.
We have a question that came up about some of the information on the slide, and
Yes.
It's more of a comment, and it is, are those backwards, SE versus diff?
Oh, no, we're showing the two different single-ended signals switching.
Okay.
And then the differential is the math, so the B minus A and A minus B to give the negative and positive swing on the differential signal.
Okay, great. I think that answers it.
Okay.
So the enhanced DES spread spectrum outputs for low EMI, that's an easy one to say, right? So the DES output is a wide parallel bus, and this is kind of what we were starting to talk about earlier. And the RDS, to address that wide parallel bus, there's an RDS feature that's a receiver drive strength and has a 1.8 volt VDDIO option.
That's right. And so with the receiver drive strength reduction, you're able to reduce the EMI that's on the interface. So if you're not driving a heavily loaded bus, then certainly run at the minimum levels. And as Alex mentioned, we have the lower VDDIO levels as well to reduce the swing. And with that, you want to make sure that you have a compatible interface to the receiver output. So you'd want to make sure that your logic is running at 1.8 volts on the far end. And then the configurable spread spectrum, thanks Alex for leaving that one to me. So again, we talked a little bit about this before, and I think this was this concept was introduced in the previous discussions. What we're doing here, and to get into a little bit more detail, is the clock typically operates at, let's use as an example, 65 megahertz. So what you would want to do is, if you're spreading the spectrum, is move that a little bit by a few percent. In this case, it's plus or minus 2%. So a slight variation of the frequency over time at a very low modulation rate. And that produces the differences that you see here, the narrow band of noise if we're always switching at a constant frequency, or the spread spectrum that you see when you're slightly varying the frequency and varying the period over which the clock is switching. Remember, this also applies to the data. All the data is output based on the clock. So you'll see all 24 bits of output in addition to the clock being spread. And this has been shown to be one of the biggest benefits in terms of reducing EMI, particularly on these low voltage CMOS interfaces.
Yeah, I might go a little bit farther and say that the results we've seen is that for some applications you really do require the spread spectrum to get to the EMI to meet the EMI requirements for an automotive application.
Yes, definitely.
We had a question that came in about the previous slide, slide 12, and the question is, what is the data rate of the serialized signal over the single pair?
Okay, you're running at about 1.8 gigabits per second when you're running at the full 65 megahertz pixel clock.
Okay.
Yeah, and you can calculate this based on your pixel clock and knowing the fact that you're sending 28 bits in any payload. Take your pixel clock times the 28 bits, and that'll give you your data rate.
Oh, got it. Let's see, we just had another question that came in, and that question is, customers are asking for full 1080i and 1080p HD support for various applications. When can we expect to see this support, and what level of cable reach are we targeting?
Well, the products here are targeted at the automotive application space, and in automotive, the 1080i is pretty far out for an automotive application. We do have some products in development that are high def that'll be coming out in the next year or so. So I think the best way to answer that is to say stay tuned and you'll see more products in that area. Okay,
fair enough.
So let's talk about another feature, which is the enhanced built-in self-test. We talked a bit about this in the last webinar, but the BIST is a very useful test that is used by designers and in manufacturing, particularly for the factory test, so functional EMI cable testing, the system startup as a link check, and also now for diagnostics, for looking for problems and system checks. So one of the results of this enhanced built-in self-test is now designers can look at it not just during the development and prototype stage, but actually use the BIST during operation of the system. And that's because it's the user controls the duration, and the pass pins can toggle on payload errors. And then finally, the final results are held on a pass pin. So if it's fail, you see that means you encountered one or more payload errors. And if you pass, that means you're error-free on the PRBS test. So this is actually a very exciting feature that customers are designing systems now to use.
How often is the built-in self-test feature used?
Well, as is noted here, it can be used in a variety of places. We use it in our own development when we're testing to ensure that we're meeting the bit error rates that we want to. It's a very quick and easy way to do a self-contained test. And I think that's the key point here, is that it is self-contained. It doesn't require any kind of generator, and it doesn't require any kind of measurement system on the far end. So the customers will use this as they're in production line when they just want to test the interface between the serializer and deserializer without looking at any other parts of their system. They'll use it for diagnostics for the same reason, to kind of help debug, to isolate where a problem might be occurring. And then finally, because we have the user control duration now, we can make this testing very short. The user can define how long they want to run this. So it's very convenient to now run this at startup. So as the car is turned on, checking all the interfaces, the display interface can be checked as well.
Okay, great. We had a question that came in too, and the question is, what's the maximum cable length over a Cat5 cable?
We're targeting upwards of 10 meters over a Cat5 cable. Just keeping in mind that for the automotive, typically what we'll see is higher end cables being used, usually something like a Rosenberger-Leone cable assembly. So that's what a lot of our testing comes down to. In addition, with just talking about cable length, we find that in the assembly of the automobile, they often need to break the cable. So there'll be multiple segments. So we also do testing and modeling to guarantee that with cable break, so with multiple interconnects throughout the cable, that we'll be able to still support the full 10 meters and above.
Okay.
So the other part of that, I think, is that it depends on what pixel clock you actually use. Right?
That's true. So if you're running at a lower rate, then you can extend the cable length beyond the targeted 10 meters.
Okay.
So now let's talk about a few more of the enhancements on the part. The integrated termination resistors that are really for the reducing the complexity of the board design and allowing for lower cost and less board space. I'll let you talk about the rest.
Oh, sure. Now on the, we have integrated the termination resistors, as Alex said. Now what we've also done on the deserializer, we've provided a common mode termination filter pin. Let me explain a little bit about that. If you had external resistors, you'd have a common mode point available. Because we've integrated these, we've pulled that point out, and this allows the user to connect the common mode to a capacitor to ground and stabilize the common mode voltage. This is really important in the automotive industry in particular because they do what's known as a bulk current injection test, and this can move the common mode all over the place. And what we want to do is stabilize that so that we guarantee the integrity of the data being received under these harsh testing conditions. We mentioned a little bit earlier both a 1.8 volt VDD-IO as well as 3.3 volt. And this is done for a couple of reasons. One is to take advantage of a lower interface level, better compatibility with the downstream device, and if you can run at the 1.8 volts, again, that lowers the EMI. The deserializer outputs have some configuration options. This is some feedback that we got from customers that they like to be able to have the deserializer outputs in different states when in a power down condition. So we've added some configuration. So the video outputs, that's the RGB, can be either tri-state or low when the power down is asserted. And the P clock can be tri-state or low, as well as you have the option to run off of an internal oscillator. So a clock output will always be provided regardless of whether there's an input.
So that actually allows people to support different, say, system designs, right?
That's right, yeah. And in some cases, the downstream devices need to have a continuous clock, so that provides a continuous clock to the display. And finally, we touched on this briefly, is the receiver equalization eye monitor outputs. These are the couple of test outputs that we talked about earlier, where you can look at the output of the internal equalizer and see how well you've tuned your equalizer for the cable that you're driving.
So in summary, let's talk about the key features of this part. It has a single pair video interconnect, which is very important for automotive applications. It supports a wide range from WQVGA up to XGA displays. It has the support for 24-bit color and video control, and also signal conditioning for extended reach. We've added a number of different features to improve the EMI, enhance the BIST mode, and we've built off of a proven, reliable, and robust SerDes structure. And finally, we've got a roadmap to embedded control and more. There's a lot more coming from us. So let's talk about the family of products that we have. First is this part we're just introducing now in the FPD-Link II family. It's the DS90UR905-906. And this part really is targeted, like I mentioned, at the 65 applications that require a 65 megahertz pixel clock. At the same time, we're going to be releasing a DS90UR907-908. The main difference there is that instead of using the LVCMOS parallel interface, the other SerDes set will be using an FPD-Link interface. The FPD-Link interface allows you to connect to different displays and to different video sources, and really the FPD-Link interface allows you to take your EMI even to that next level. It provides a much more reduced EMI profile. There's the DS90UR905-124, and this is the part that we talked about in the last webinar. It's popular for 18-bit color depth applications. And the DS99R421 is now going to get a complementary DS99R124. And this is really our set of bridge chips that bridge from an FPD-Link to an LVCMOS interface, or vice versa, from LVCMOS to FPD-Link. And the first part in this family was the DS90C241124, which is popular for lower clock rate applications and really in camera applications too. And coming soon, we have a number of new parts that'll offer more features like faster pixel clocks, higher resolution, less wires, and other features like that.
Okay, great.
So the next slide here, we're going to give you a link to the portal for the automotive products from National Semiconductor. This will allow you to see not just our FPD-Link or SerDes parts, but also parts for power and audio that'll go into safety, powertrain, LED lighting. You can see the full breadth of the features that we have for automotive applications. And now in summary, we wanted to make sure that you knew which automotive applications are targeted for the DS90UR905-906. So Sue, if you would just kind of mention those.
Sure, and so let's walk through those. It's a central information display, rear seat entertainment, as well as instrumentation, and those applications which are really looking for some 24-bit color support.
We want to talk about the key system benefits.
Again, really what we're trying to do is continue to drive video data, now taking it up to a higher rate, higher color depth, over the same single differential pair and long cables, and maintaining low EMI.
And then to go into the main features and the key enhancements to the chipset. And we have these listed here, and you can go in for more detail on that, both in the webinar and also off of the data sheet. And speaking of which, for more information, you can find our DS90UR905-906 datasheet that is on the web on the product folder. There is a feature website, the analog/displays, that goes into more detail on the FPD-Link products. And there's a number of application notes that Sue and her team has put together for these parts. And you can refer to our previous webinar on the FPD-Link II DS90UR12241. And also for evaluation, there's an evaluation kit. If you could tell them a little bit more about that.
Sure. There's a single serializer board and a deserializer board with a 905-906. There's power circuitry on board. We provide a USB cable interface by default, and there are options for other cable interfaces as well. And this is really used for the benefit of you guys to get a first look at the performance of the chipset. There are some header interfaces where you can connect this to a video source and to a display to check things out.
Great.
So also, I think it's important to realize that you could use this. You can use other cables than the USB cable with
That's
this,
right, yeah. There are options to have this with the SMA connectors or with the Rosenberger-Leone cable assembly.
So thank you very much for your time. I hope that you found this to be a useful presentation, and thanks, Tom.
No, thanks to both of you. And if folks have any questions, they can feel free to contact both of you as well, too.
Absolutely.
Right. Okay, great. Well, thanks, everyone, for joining us today. A few last things in closing. One, there's a short 10-question assessment associated with this webinar as well. If you can take a few minutes to complete that, to find out what you learned in today's session, that would be great. And then, as always, we're really looking for your feedback. There's an evaluation associated with this webinar, too. You can also take 4 or 5 minutes and complete that to give us your feedback. We appreciate that, too. Beyond that, thanks again, and enjoy the rest of your day.